Good morning, everybody. Buongiorno a tutti i nostri colleghi italiani, i nostri amici italiani. And welcome to this webinar we are co-hosting with Teledyne E2V Space Imaging. The webinar, you know, it's centered on how to bring space imaging experience to commercial space. And together with us, we have Jerome Pratlong, that is one of the chief engineering in Teledyne E2V Space Imaging. Jerome would do a quickly introduction to what is the programs and where they come from Teledyne Imaging, E2V Space Imaging, sorry. Then we will have a short introduction with the products and the application they have, the technology innovation that Teledyne keeps on bringing on its product, and a bit introduction on how they support commercial missions. Then we will have a short, depending on how many questions we have, Q&A session for the people who's participating in the webinar, who's seeing the webinar. You can directly write questions in the chat box that is included in the webinar panel. I would do the questions later, asking Jerome what is written from you, and then Jerome will simply answer them. I guess that you probably know Images. Images is a company in Italy founded in 1994. We are one of the top player, even if not probably we are the toppest player here in Italy in machine vision distribution. Teledyne, it's one of our first, if not even the first, of our suppliers, probably the biggest one. We are involving with them since the beginning of our era, and we started some years ago with Teledyne E2V, especially in the space market, where E2V is one of the leaders in everything. So we decided to have this webinar that can introduce to people in Italy and also around the world, because I saw that there are some people outside of Italy, don't know exactly from where, but probably all around the world, really. So to understand which are the products that the Teledyne E2V sells and produce, and everything that is linked to this new and brand new also application field for images. I can tell you that I have finish my very short introduction, and then I just have to let Karin Barnes, that is connected to the company, to the webinar together with Jerome, and I can have them, here it is, start the introduction and the presentation from Jerome. Karin, when you want, you can do anything. Okay, that's right. I will simply disappear, but I will stay here and then come back at the end of Jerome's presentation. See you later. Jerome, it's also up to you now.
Thank you. Welcome, and thank you for joining this webinar. For during that session, we'll talk about Teledyne large space imaging experience and how we propose to bring it to commercial space. Today, I will discuss about the Teledyne. Teledyne is quite a large company, and I will focus on the part that is specialized in space imaging solutions. For this part of the Teledyne business has a quite wide range of technology detectors, and we cover from X-ray to infrared via different technologies like CMOS, infrared MCT, and the CCD foundry, but we also have a fab in-house. But we also go beyond the imager with some microcontroller or processor memory converters that are usually used at the front-end electronic and higher level for data processing. And we also provide system solution via cameras. We also provide services like consultancies Therefore, it's quite a wide range. And today, really, the webinar will focus on the CMOS aspect, therefore the visible range of detectors. And what is here mentioned at COTS, but I think the best way to represent that or to mention it is commercial space. And we are going to see what is the value proposition we propose here in this commercial space environment, followed by products that we think are extremely well suited for this sort of market. And we will end with a technology aspect. For Teledyne, as a quick reminder, for space is a big player with a global partnership over more than 40 years of space program and be part of the ecosystem. And that goes from institutions like ESA, NASA, JAXA, and so on, to smaller companies that are actually more commercial based, commercial space based, but also, and as importantly, collaboration with universities. And for just to give an example, today we've got in GeoLeo more than 140 missions with 0 fails. So that is something that is very important to us, and that drives our proposition value. Therefore, briefly, the proposition value that we have is really focusing on the gray box, is to try to provide a solution based on our experience, standard as well. As I said, to date, we have no fail in space, and it's something that we really want to keep. Therefore, we are proposing an intermediate solution in terms of pricing between pure cost, that we don't do, and institutional type approach that are heavier in terms of qualification in general, and makes the price to go up. By being intermediate, what the customer can get from that is a solution less risky, reduced in terms of development time compared to an institutional program, and the confidence with Teledyne that we will deliver stream device that are suitable for space. Worth mentioning is that today we propose access to industrial type detector that also we call MVS for machine vision sensor from Teledyne, but also detector that have been fully developed for space, or specially developed for space, with space application in mind. And we will see through this presentation that sometimes is worth considering this detector that might look a bit more pricey in a way at the beginning, but add so much advantage at the global solution or payload solution level that is probably worth thinking, and I will go through some example. Therefore, our value proposition is a value pricing that includes a device with a given spec, qualification report, assurance, and technical support up to 50 hours. Therefore, what do we mean by qualification route, and how it differs from an institutional market? Therefore, in terms of pricing, there is very much two aspects that build into the cost. Is the volume of detector requested, and that is a generic, well-established problematic in semiconductors in general, not just imaging, and the level of test and qualification requested. That's our two major. Therefore, in terms of qualification, what we propose is to go through the classic tests like environmental, radiation, and batch testing, but more as a delta. Delta compared to what? Delta compared to tests that have been already done on these detectors, and also a delta compared to the understanding of the application, length in terms of duration of the mission and things like that. And that allows us to get a minimum tailored approach that, in one hand, guarantee a low risk for the customer, but also for ourselves, while reducing drastically the lead time and giving this confidence. The report issued after all these tests are shared with the customer and delivered with the hardware of a contract that is a detector or more. Obviously, we are very familiar with a full extent of this qualification route. And if in a particular case, the customer wants a particular customed, let's say, qualification, we will be always open. And although I will not go through here, we've got all the capability to do all these tests in-house, is fully integrated. Therefore, from this value proposition or business model, I will go through certain products. One, the first part will be the imager from industrial or MVS, that sometimes we call off-the-shelf. And then I will go for the more specialized detector that we developed through institutional missions. Therefore, that is a graphic of the machine vision sensor that are developed within Teledyne E2V. It is quite a large number with quite a varied proposition, from a pixel pitch varying from 2.5 to 10 micron and a format up to 67 megapixel. Therefore, it's quite a wide range. We don't propose to screen all these devices, but more a selected of few. And the reason is back to the question of volume and the fact that to get the best price, it is important that we focus on fewer detectors to get the best value. And the one that we see as the more interesting for commercial, and that's the one I will focus my presentation on, the Emerald in 2.5 and 2.8 micron, the two first columns, along with the Snappy that are in the first column just below the Emerald. They are similar, just a format difference. The Lens that are the purple, dark purple one, in the 5 and 6 micron and even 10 micron. They differ from the Emerald, obviously, by the pixel pitch, but also by the frame rate. That's another aspect that could be of interest in commercial applications. And I will focus on one that is a bit particular in the sense that it's not 2D, but a 3D imager, which is the purple one in the 10 micron column that is called Hydra 3D/3D Plus. This is more for 3D imaging and direct time of flight. Therefore, that kind of target a different kind of mission that also interests commercial in general. In terms of Emerald sensor, is probably the one with the most format availability, from 2 megapixel to 67 megapixel. As I mentioned, is a 2.5 and 2.8 global shutter pixel, usually refer or used for high resolution type mission, with a lot of features embedded in these detectors, like multi-region of interest to speed up access or targets research, real-time high dynamic range, and then a certain number of statistics that you can get directly out of the sensor. Therefore, I don't intend to go in the detail of each, but it's just to give an overview in the few minutes we have. Therefore, here are a bit more details on this Emerald. Oops. Therefore, the 36 megapixel and 77 megapixel, these two detectors that actually are available as a kind of same format. Is just that the 36 megapixel has access to less pixel array, and therefore becomes a bit cheaper than the 67 megapixel. They are quite high resolution, as I said, due to the small pixel pitch with a large format in general. They are quite high speed for the format. That's something we got to keep in mind. Even if 120 frames per second or 90 frames per second for 67 megapixel might sound a bit low, it's still a lot of pixel to read out. Therefore, it's in that respect quite high speed. There is different grade of performance following the mission and the need to not overperform where not needed. And in terms of performance, it's quite a low noise high dynamic range because it's using a global shutter technology that maximizes the full rail capacity, while as you see here, the noise is quite low, around 3 to 4.5 electron. And as I said, there is a lot of features embedded in this detector. They are not just detector, but they have a lot of statistics and all that type of post-processing already embedded. Snappy, real difference with the Emerald is, or the main difference, let's say, with the Emerald is the format. Emeralds are more square type detectors, where here they are rectangular, which might fit better some application, and is a 2.5 only pixel pitch, which probably doesn't make it too much difference with the option of 2.8. Again, in this type of detector, there is a lot of features. The multi-region of interest is also there as the HDR, same as Emerald. You've got also option of binning, subsampling, and again, more processing comes with these sort of detectors. Lens, before lens, yes. Sorry. That's fine. Lens is a slightly different detector compared to the Emerald and Snappy, in the sense that the pixel pitch is bigger, the smallest is 5 micron, and the biggest is 10 micron. Therefore, again, that is not necessarily bad for space, in the sense that in many applications in space, there is a lot of light, and there is a need for bigger full well, which usually in CMOS come with a bigger pixel. There is still a reasonable variant number in terms of these detectors from 1.3 to 11 megapixel. Therefore, if we go to the next slide, yes, you can play. Sure. You've got a table, therefore that's a film taken with this lens, just to show the speed aspect of this detector, of the capability. But as you see on the table, if we look at the 11 megapixel, which is quite a big size, we can see that it can run much faster than the other detector, up to 610 frames per second, with quite high QE and high dynamic range for industrial detectors. Therefore, that is also another detector that we foresee as the possible interest for commercial application. Therefore, that's where the industrial type detector. Again, I can browse quite quickly through the specification. It is more an introduction, and we are happy, obviously, to share more details if at the top level one of these detectors are of interest to you. Now I will move to the more specific to space detectors. Oh, sorry, of course, one. Yes, the 3D and 3D plus detector that are for 3D imaging and direct time of flight. Therefore, as opposed to the 2D array, it is very difficult actually to give a table of performance, because this detector are based on a certain setting that must take into account the application in terms of distance, in terms of object reflectivity, object that you are looking at, and environment, context, laser power, and so on. Therefore, it's way more difficult to derive a performance that is generic. And we will see that in the next slide. But these detectors that are have, let's say, been built across years, and these ones are the latest version, with specifically long range and large field of view, And that is based on a technology that we call the Aero, that is patented, and that has the advantage to work and improve the sensitivity of a detector, at the same time as reducing drastically what we call the transfer time. And by reducing the transfer time, it means that we can get to higher resolution and therefore longer range. Adaptability, it has in mind a certain number of user cases that are more industrial based, but it shows that it's got some adaptability and flexibility for different missions. Again, things that we need to assess individually, of course. It has also a non-destructive readout approach, and that is to do reliable distance measurement by continuing of integration while reading the pixel or the light coming in. It has also, it's based on a three taps pixel. For the ones that are familiar with CMOS pixel, let's say it's the equivalent of a transfer gate, and instead of having one, you've got 3 of them. And that is quite a differentiator because what it means that this sort of detector have to deal with the fact that you send to an object a square wave, and you measure the reflectivity of this square wave, and you do the delta between the two in order to estimate distances and therefore reconstruct a 3D imaging or measuring simply a distance as a LiDAR. To do that, the main thing is to take away the background light, because the laser is still extremely small in terms of power compared to the ambience. And usually, when you don't do with 3 taps, you need to take 2 pictures. And if you got something moving, then you will have artifacts. Here, you can remove the background within 1 image by using this third, let's say, tap, where the background is collected and subtracted automatically to the rest of the image. So that is really a big differentiator, even compared to detectors done in indirect time of flight by the biggest company in the world that's selling in very large volume for CMOS. Another aspect that is also quite important in this for these detectors is if you got a system where you need more than one indirect time of flight or laser working at the same time to look at different aspects, they have features built in to understand the interference coming from other systems and making sure that they are not polluting the acquisition. Therefore, that's quite also powerful in a busy environment, let's say. Therefore, as I mentioned, it's very hard to have a standard data sheet for this sort of detector because they depend on a lot of things. And also, it's also important to be able to have an evaluation on this detector. Therefore, we do provide, actually, like for the 2D, I didn't mention, but we provide demo kit for these detectors. But in particular, for the 3D time of flight is quite important. Therefore, we provide evaluation kit, reference document, okay. But more importantly, we have internally a model simulator that can take all the inputs considering the mission, like distance, field of view you're interested, light budget you have, object reflectivity, and so on. And from there, we calculate the exact operating point for the detector, but to reach these targets, obviously, if it's not outside the range of this detector. We have also, and that's quite important, is a laboratory to test the detector in the condition, and that is accessible to the customers. Therefore, that means the customer can come and trial the detector in the laboratory and see in a more real condition how the detector behaves, and obviously if it is suitable for their application. Okay. Therefore, from there, I mean, the last slide on 3D plus, 3D plus Hydra was on the, let's say, machine vision sensor. And now we are going to go into detectors that have been designed for specifically for space, with space application in mind. They are radar, as the opposite of machine vision. And these detectors are designed on silicon, working, for some even in production. Therefore, all of that to say that NRE is paid for the development of this detector. Therefore, we are in a kind of similar situation as the machine vision, in the sense that we are back to the qualification route we want or not. Again, once the detector is developed, the qualification volume plays a big role in the overall pricing of the solution. Therefore, I think going through that detectors, I try to put the emphasis of what do they bring and how they can impact in a positive way the overall payload costing and complexity. Therefore, the first one is our general purpose CMOS, CS120, is a 2K by 2K, 10 micron pixel pitch. And it exists in 3 variants that are based on different full well capacity. For the what we call the low noise is 45 or 41. Let's see from there. So 43 kilo electron, 60 kilo electron for the large swing signal, and 100 kilo electron for the extra large signal. It is often that the 100 kilo electron is selected simply because, again, in space, usually there is a lot of light and high full well is welcome. Why we call the first column low noise is simply because in this detector, there are a simple 5T type architecture for the pixel, and the gain for the full well is directly proportional to the noise floor. Hence, as you decrease the full capacity, you decrease the noise in a kind of linear fashion. Therefore, that's why we call this one low noise. Therefore, the first column is usually selected more for the application where the noise floor is more important than the full well, while the last column is where the full well capacity is the more important parameter. All these detectors today are at TRL6. We expect the XLS, the extra large signal, to be TRL6 early next year. And we expect to have the first TRL line next year. We have already developed, and they already exist, 3 packages. A standard one that is a ceramic type package where we can place a window, filters, what is needed. Below, we can see a sealed Peltier package. That's for application that need cooling. Therefore, typically, that can go down to -30, -40 degrees. Probably especially interesting if you are looking in the UV or deep UV. And we've got also this probably, I don't know, so interesting for commercial, but is a free-side buttable type package. Therefore, in general, suitable for people trying to build a focal plane to obtain a bigger array. Therefore, the gap between the package can be very small, around 500 microns. Therefore, you can build a quite large array with, or large focal plane with a high fill factor at focal plane level. We propose also, like for the machine vision sensor, a demo kit that is also compatible with another variant that is CS220, and we'll talk about it a bit later. As you can see, we backfin all this detector, therefore their QE is very high, even in the near infrared, but we will just see afterwards how we increase even further this type of response. Therefore, this detector is available as a standard product based on stock, and the QE that is presented here is a typical QE part of the standard offer. But as we are going to see, we can do over QE might that is being needed. Just to mention also that this detector is today selected for the Copernicus new generation CO2M, but to say that this detector is going through a large amount of testing and qualification for ESA. Therefore, it's quite a robust detector now. Therefore, that is the variant I was just discussing, the CS220. Therefore, the 220 is exactly the same in a way than the CS120 in terms of type of pixel, 10 micron pixel pitch, 2K by 2K. It works in rolling shutter, global shutter, all the usual features that you can see in detector of industrial. However, it's the extra large full well version with 100 kilo electron, because today is the one we foresee as the more interesting for customers. But the difference is that we brought what I already mentioned a bit with the 3D Hydra 3D Plus is the Aero technology that originally was developed for space applications. And this Aero consists in applying what we call the reverse bias at the back of the detector in order to enhance the performance of a detector in near infrared. The limitation in near infrared for CMOS detector is rather simple. If you want to increase your sensitivity in near infrared for CMOS, you got to get a starting material where you build your detector on, the thicker you can. Unfortunately, and compared to CCD, the voltages in CMOS are quite low. And therefore, it's very hard to deplete the photodiode and the material below fully. And if you don't deplete fully, what happens is that you got a problem of what we call MTF, meaning that you don't know the electron collected in a given pixel if they are meant to be for the neighbors or not. Therefore, in order to enhance the depletion, we reverse bias, and therefore we apply a large bias at the back without current. Therefore, it's a very simple bias to build. And that way, we can go very thick while maintaining this MTF performance. Therefore, today, the top graph shows measurement in line with models of QE. Therefore, if we look at the CS120 that does not have this Aero component or technology, you can see if we look at 950 nanometer, that the QE will be around 20% or less. Whereas today, we have demonstrated on a 33 micron epi thickness that we can go up to 60%. Therefore, that is a big increase in your light sensed, and that means a huge increase in SNR. While if you look on the last curve, the MTF curves, that the MTF is kept above 0.5 and actually quite uniform over all wavelength, showing full depletion. Why we do that is because if you look at the curve of QE, we propose in backfin device various AR coating, and that is to enhance the performance across the wider possible range of wavelength. And if we look at the CS220 broadband, the purple curve, we can see how much the knee point has been shifted, and obviously how much the QE increased in the near infrared. Now, if we were to imagine combining that with our UV coating, that is going down to below 200 nanometer, and we were to use Aero, that means for a 70% QE, which is slightly better or even better than front face without microlens, we could go from a bit below 200 nanometer to about 1020 nanometer in one detector. And that's where I think the added value is, knowing that is a CMOS. That means compared to infrared detector that can go in the visible, there is no need of cooling or things like that complexify the system and the cost. This technology is now TRL6. Now, I'm going to combine, or try to combine this, let's say, technology increasing the sensitivity of a detector in the near infrared with another type of development that, again, development that exists, detector that exists, that doesn't need an NRE, is what we call the large format CS300 family. Before this detector is a wafer scale detector of 9,000 columns for 8,600 rows of a 10 micron pixel pitch with a dual gain for high full well and low full well, or let's say high full well and low noise. It exists with all the classic features: rolling shutter, global shutter, high dynamic range, a selectable bit depth operation for the ADC, and that is mainly to deal with applications that need a bit more frequency frame rate or a bit more accuracy in terms of low noise. It's a high frame rate using CML output, running relatively fast at 2 gigabits per second. But we got to keep in mind that this detector have a bit of data formatting. So the data comes as streamed, meaning that the clock and the data are fully embedded, which means that at the receiver end, what the FPGA has to do is simply to recover the clock from the data. Therefore, although it's very fast, there is no concern or constraint about front-end electronic in terms of setup and hold at such frequency. Therefore, it's already pre-encoded and formatted. The QE is what we already discussed. Technically, this detector has been designed to be cooled as well. Therefore, it's designed to operate down to cryogenic temperature. Today, our experience in CMOS is down to minus 130 degrees. That has been achieved on a detector that is today used in a telescope for a TAOS 2 mission. Okay, we've got two packages. We've got test sensors, temperature sensors, sorry. And the same as the CS120, CS220, we've got the version without IRO and with IRO. Therefore, that is a generic presentation of this detector. So if we go to the next one. Therefore, that is a kind of reminder of the various operating mode. As I said, rolling shutter, global shutter, simple global shutter. The difference between the global shutter, DDS, and simple global shutter, it just means that in global shutter, we don't automatically remove the reference for the pixel, which end up with being a bit higher noise due to what we call the KTC noise of the reset. By doing digital double sampling, then you can remove it and get to a noise close to the rolling shutter. Rolling shutter operation is the mode that will always give the lowest level of noise. Simple global shutter means that we don't remove that noise. The interest of not removing that noise, in some applications, the noise floor is not so interesting, but and therefore, simple global shutter can bring a higher frame rate compared to a global shutter with DDS. Therefore, that's a bit of a trade-off. We've also have the operation mode of staircase operating mode, which is a multiple non-destructive readout, which also is often features in machine vision type sensor. In terms of gain, there is a variety of programmability between the gain in the pixel and the gain in the column prior to the ADC. I didn't mention that all these detectors are digital, meaning that they all have a column ADC approach. There is no analog type detector here. Therefore, combining all this gain, the noise can be as low as 1.6 electron, and with a bit of multi-sampling, which actually exists in this detector as a feature, you can go a bit below 1 electron. Therefore, it depends on the application and the need. And as I said, the bit depth is 12 or 14 selectable following the need again. Therefore, that is a summary of the performance. I won't go too much in details here, but what is important is that there is a gain in the pixel with 2 full wells, 140 kilo electron, that is measured value. Therefore, for a 10 micron pixel pitch is quite a lot. While the low gain mode, the high gain mode, give a noise as low as 2 electron, below 2 electron, and today the expectation is precisely 1.6 electron, which is the minimum to start to be able to apply oversampling, to be able to go sub-electron. Therefore, the high dynamic range is 95 dB, typical, and the rest are a bit more detailed, I guess. Note that the power dissipation as a full features is 6 watt, but there is lower power mode down to 2 watt following the need. For last, let's say, slide on the detector itself, it's a 2D, therefore it's a wafer scale detector, which means that it's built in what we call in CMOS 2D stitching. For people who are not familiar with that term, 2D stitching means that the detector is so big that we cannot fit in one mask set for fabrication. Therefore, what happens is in that mask set, we design the repeated block only. And then during manufacturing, the blocks are repeated, like printed, as many times as needed to form a full detector. Therefore, we can see that with, for instance, the pixel array, where you got the acronym MC. Therefore, each square is actually a repeat of the same pattern that are, in that particular case, pixels. And in the table, we call that unit. That means the minimum unit for this pattern repeat is 1.5K by 1.5K column rows, but we can do the others. The good thing about 2D stitching is that once that is done, it means that any format, there is no need to repay for the mask. The only thing we need to do is to order new wafers. Therefore, in that respect, that means, again, all this format does not come with a new NRE. They are part of the platform. Therefore, that's can be quite interesting if you got an interest in a specific size. Therefore, it's a wafer scale. The first version we have, the CS303 and 304, they exist. They are in silicon. They are on test, and but we can go slightly higher. Obviously, in this sort of size at wafer scale, we have to consider yield as well. Therefore, bigger they are, probably less low cost they are. That's probably the thing. It's a very flexible platform. The periphery is done to be able to put in a pixel as small as 5 micron square. And therefore, after that, every bigger pixel pitch than 10 is possible. Obviously, if it is a fraction, a multiple, of 10, it's easier and requests less NRE than if it is an odd number. Therefore, if I look now at this discussion we had about QE extended in the infrared in the UV and this large format, how does that help potentially for applications? Therefore, the first thing that we noticed part of the market, institutional or commercial, is obviously about data service. And to do the best data service possible, a lot of data needed to start with, and a lot of data on a given object. And one way to do it is to see the object with as many possible wavelengths. And that's where multispectral and IP spectral type detector are becoming more and more demanded, because they can provide a huge amount of information on a given object and therefore help with a better data service provider, in the sense that there is more information that are extracted from the object and therefore better decision can be made. Now, if we look at a large array like the CS300, and we imagine that we've got a gap of 2.5 millimeter per filter, which is not aggressive at all. People can do much lower, much smaller than that. That means on this detector itself, we can put more than 30 filters, therefore more than 30 specific wavelengths. And now if we combine that with an aero version that can go, let's say, reasonably up to 1020, obviously it can go a bit higher, but the QE will start to be a bit low, maybe. That means that these 30 filters or more can be applied on a very wide range, typically from 300 nanometer to 1020 nanometer. But again, if we accept a slightly lower QE, it could go down to 200 nanometer or a bit lower. Therefore, in a single silicon, no need of cooling or specific cooling, we can address a wide range of wavelength, yes, in one piece of silicon. Therefore, that's the sort of application where this sort of device in commercial could be actually extremely useful. Another aspect is hyperspectral. For hyperspectral, usually has a slightly smaller format with a slightly, let's say, a bigger pixel, although the pixel can be recovered from a binning, externally bin version. But today we have already developed for another application, but the performance are very interesting for hyperspectral still. It was for the Lightning Mapper for NASA for their next GeoXO mission, and we developed a demonstrator with a 24 micropixel pitch, 512 rows for number of column is obviously to be defined by the application, and with a readout that was done at the top and at the bottom, and we were able to read this detector at a speed slightly higher than 2000 frames per second, which is quite fast. Obviously, in space, that might be a bit too fast, and obviously we can slow down. Now, if we think about airborne application, that start to be the right type of frame rate. Obviously, it can be stitched in column-wise. Hyperspectral, in general, based on 512 row of such large pixel. And in column, it may depend a bit, but because we read with ADC column, the number of columns doesn't matter for the frame rate. We can add as many columns as we want. It will still be the same frame rate. The frame rate is only dependent on the number of rows. But what is important to realize is that hyperspectral work with very narrow bandwidth wavelength, and especially when you get to the near infrared, the bandwidth can be as small as 2 or 3 or 5 nanometer. Therefore, very small. And that's where, again, the aero and our type of AR coating can come in. Because this sort of detector with in the near infrared or even front face, because here we are talking about back face device, have what we call the fringing effect. Therefore, the fringing effect is what you see on the QE curve, top right, where you see this kind of oscillation starting where the knee point of the roll-off of the QE appears. And that is simply what is, I try to draw very coarsely in the drawing at the bottom left, is the fact that the light coming in bounce back to the other side of the silicon and come out. And when it's coming out, it is merging with the incoming light in a, not random way, but in an interference. And that gives this oscillation. And that is problematic because this oscillation are bigger than 5 nanometer. Therefore, that could be actually a killer for an application in this region. Therefore, what we do is 2 steps. The first one is aero. having IRO, as we can see, we got a higher response in infrared. That means the midpoint where the QE starts to roll off goes further to the right, and therefore the oscillation starts later. That's one thing. And as you can see, the frequency becomes higher, right? Therefore, closer to the narrow bandwidth of the application. And the reason for that is simply because the material is thicker. But on top of that, we apply what we call a graded AR coating that reduces the amplitude to almost nothing. And that's this technology, IRO plus this graded AR coating, enable actually the hyperspectral mission in the near infrared. These fringing are really catastrophic in hyperspectral if they are not managed and not thought about at the beginning. Therefore, that's one of the things by designing for space. That's sort of a specialty where we have been experienced. Now, I'm going to give another example, which is one of our detector that is quite popular, is the CIS-125, and is what we call a TDI, or CCD on CMOS. Therefore, it has 4 panchromatic channels at 5 micron pixel pitch. Therefore, panchromatic meaning without filter. Therefore, they integrate the full spectrum. And then we've got MS. And this MS have the filters. For each MS corresponds to a certain wavelength. And their pixel pitch is twice the pan, for 10 micron pixel pitch. Each pan or each MS are subdivided in 2 pan and 2 MS each. And that is simply to be able to enable a customer to bin or to sum in a digital fashion the full well of 2 pan in order to increase the total full well, while the noise increase only in root square fashion. And that means that the overall dynamic range can increase compared to having a single pan. But that is just optional. Therefore, in terms of performance, the pan are 30 kilo electron, MS 80 kilo electron, and the line rate on this detector is 40 kilohertz as maximum, but the default operation is 14.7 kilohertz for all the lines. The readout interface is exactly the same as the 2D array, which means that we have developed an interface that is common to all our detectors in order to simplify the integration at the system level. All this pixel comes with anti-blooming, which is important for this sort of detectors where the contrast with very bright scene can happen, and we have to be able to recover quickly, and therefore anti-blooming is there for that. Compared to CCD, this detector comes automatically with bidirectionality. That means when with a CCD, you need to have a CCD mounted, duplicated, in order to be able to activate one when you go in a certain direction of scanning of the Earth, and then you have to activate the other one when you move around. This one is just a reprogrammation of the SPI, and it can go in both directions for top-bottom or bottom-top by simply reprogramming the SPI. Therefore, that enables to save per default 1 detector if we compare to CCD. Yes, they are radiation tolerant, and we do also offer to integrate filters. Therefore, we've got a family of this product. They are there. The point to note is that the difference is mainly about the pan pixel pitch, where most of them are 7 micron. It's only the CIS-125 that went down to 5. And that is obviously for GSD reason. but also the number of PAN of MS that vary a bit following the version. They are all of the same family. That means they have all the same interface, despite the fact they have a slightly different name, and they are compatible with each other. Therefore, what is this technology? Is a technology where we try to get embedded in CMOS a key feature of CCD, which is the charge domain movement across pixel. And when you you move a charge in the charge domain, and we don't build a voltage like we do in a 2D array standard pixel, it means that each row is integrated and the signal is passed from row to row without additional noise. Therefore, the great advantage of this technology compared to a 2D array is that from a pixel perspective is noise-free. And that is the key thing. Obviously, compared to CCD, the CMOS had the usual advantages, is parallel readout and higher speed, lower power, since compared to CCD, it doesn't need high voltages. And obviously, once you're in digital, after the ADC or the converter, as we call it, we can do a lot of processing when we want to. Obviously, the CCD remains slightly better for some one parameter, which is the dark current, which is always a bit better on CCD than CMOS. But because of the frequency used for this device, the dark current has little impact on the SNR still. Therefore, that is a bit of the advantage at system level. Therefore, because compared to CCD, because they are fully digital, it's simpler to integrate, no need to generate high voltage, to control them, to control the slopes and so on. In terms of focal plane, as I say, it's quite a great simplification because you can have a huge amount of bounds on the same detector. But also and more importantly, sorry, as the satellite cross the, let's say the trajectory of direction, when you scan in one direction or the other direction, you don't need a second detector to do that. You have a bidirectionality within the detector. You can do some summation, especially of certain feature like half pixel shift, and we see the importance of that in a few slides. And compared to CCD, is considered as very high radiation tolerance, because one of the difficulty of CCD with this sort of technology is that the oxide used for the gate is quite thick and therefore subject to radiation damage way more than CMOS. Therefore, that is a very quite a detail of how the pixel is done. Therefore, I'm not going to spend too much time, but I wanted just to introduce the fact that our pixel are done with 4 gates per pixel. And the importance of that is that because we've got 4 gates, we are less sensitive to motion smearing in an application because we can deal with the MTF down to a quarter of pixel that is represented by a gate. Therefore, by having 4 gates per pixel, we have a less sensitivity to these motions and therefore greater performance in overall for the MTF along track. But yeah, that's what I wanted to use this slide for. Now, I tried here to try to illustrate why this detector, although dedicated for space, and one might think a bit more pricey than off the shelf, what are the advantages and how that can affect drastically the overall solution and therefore the overall cost for a payload or a satellite. Therefore, if we imagine that we focus on a PAN and we really want to look at the equivalent of a pan in a standard 2D array that is using a 4 or 5T pixel, like the CS120 or CS300, for instance, or the MVS detectors. And we assume that a pixel pitch in 2D array has a full well of 20 kilo electron is an hypothesis, let's say, just for the sake of the explanation. That means that to make sure that we got the 30 kilo electron equivalent of a pan, we need at least 2 rows. And because the TDI comes with stages up to 64, that means in a standard 2D array, it means that for each equivalent pan, we need 120 rows in total in a 2D array. Therefore, the line rate, that is for a CS125 40 kilo line per second, becomes a frame rate in 2D array of 40 kilo frame per second. Which means that for an equivalent readout, and today we use a very fast readout. The ADC, it has been published in some papers, works very fast, can convert 12 bits in a bit less than 1 microsecond. Therefore, they are quite fast ADCs. Still, for a 2D array, you will need a much faster ADC to cope with this frame rate in comparison to the CS125. Therefore, you can imagine that that is only for one pan. Then you multiply by 4, and then you add the MS, and that goes only worse. Which means that from a system point of view, what happens is, one, as I mentioned, the CS125 is noiseless charged domain approach. That means the only noise that you have is the one from the readout. Whereas in the 2D array, you have to do the summation of its rows, which means that the noise increases each time you sum a row, which does not appear in the CS125. Therefore, signal noise ratio reduction. The line rate has to be much higher because the line rate of CS125 becomes a frame rate for the 2D array. That means the amount of data and the speed will be at the equivalent way more higher again. And I mentioned the MTF. And that can be, let's say, summarized in the fact that all of that could affect also the satellite mass, actually. So if we go to the next slide, that is an example for just again, for the sake of argumentation. If we look at the CS125 today, and we want to do a true 0.5 meter GSD with a swath of 8 kilometers, therefore, here is representing a bit what will be the mass of the satellite based on a calculation from that of what the optics will look like. Now, if we take into account in this CIS 125 the super resolution, where we can take advantage of pixel shift and over extrapolation, we can have a true 1 meter GSD down to 0.5 meter GSD with super resolution. Therefore, that means not quite a true, but very close to, with a swath of 16 kilometers, with satellite mass way smaller. It's almost a shift in terms of classification of satellite. Therefore, again, I think that's kind of summarized well the fact that, yes, maybe the CS125 is designed specifically for space. It was actually designed for commercial applications. That's its origin. And therefore a bit more pricey, for instance, than a machine vision detector. But how that can help higher up in the design, payload, front-end electronic, and so on, is quite important to take that into account in the overall analysis of what low cost means for certain application. Okay. Therefore, we went through a certain number of first slides where I think the key message is that we are world leader in space imaging solutions. We have a long track record of no fail in a huge amount of missions. We have in-house a wide range of machine vision images that we can support. We've got also a very detector very much designed with space application in mind in order to make the best of other aspects of a design, including payloads, satellite, and so on, that are worth considering in overall project. And all of that in a commercial space environment are taken in, and the best detector selected for the application, on which we apply a minimum and tailored screening in order to lower risk, shorter the lead time, and keep this confidence of no fail that we have to date at Teledyne. And I will probably not emphasize enough, but the best way to get the more successful mission is really to work in partnership. Therefore, we always very keen, and we will always take time to discuss, to understand the mission, where you want to go, and try to propose the best solution. If it's a machine vision sensor, it is a machine vision sensor. If it's a more specific, it's a more specific. But we are very committed to be working as partner more than just a supplier of detector. Thank you.
Okay, I'm back. Thank you very much, Jerome. Really appreciate it. You had a very good presentation. I got really some questions. Then I ask all the participants if they want to ask something else or something more, they just have to write them down. There's one attendee that asked, would you screen devices that are not from Teledyne at all?
No, we will screen only Teledyne detectors.
Okay. And then maybe it's more, are you proposing also front-end electronic or cameras for those detectors? I should already know the answer, but better if you answer.
Yes, we propose cameras. It was not the topic of this webinar, but effectively, as I was presenting the second slide, so there is a section about cameras, and we develop camera, and we have been selected even for big missions with ESA for developing the front-end electronic. Therefore, we are definitely also providing cameras.
Okay. For all the detectors, I guess, that you presented also today.
Correct. Correct.
Oh, okay. Can you just tell us how many detectors do you already have on space?
That's a huge number. I don't know, but at least more than 140, because that's just the number of GEO LEO. But there is way more missions. Therefore, probably more than 200.
It's more than that, because most missions have more than one detector.
Yeah, on top of that, yes. And yeah, thank you, Karen. And there is more than one per mission. Therefore, it's big number. I don't know on top of my head.
Just give me 1 second. I have to open. Okay, no, that is not what. That was not a question. It was only thank you for your time. Very interesting presentation. A comment from a customer.
Yeah, it's just to mention in the news, the latest news you may have heard about Gaia, and I think it's more than 160.
106.
106 detectors solely for that mission.
Okay. So if no other questions are coming, I guess that we can probably close here. We have no other questions coming from our attendees. So I just want to thank again Jerome and Karen that was behind the scene helping us for this webinar. So thank you again from Teledyne E2V. Thank you to all the customers that were attending the webinar today, and see you soon for our next one. Thank you very much. Bye-bye.
Bye.